In this video, we're going to learn how to create and work with nullclines for differential equations. Nullclines for differential equations. So let's take a look at this problem here. We have this system of differential equations, and we want to find the nullclines and the critical points. As we go on, we'll do some other things with these as well. But let's start with finding the nullclines. The nullclines will be found by setting each of these equations equal to 0. So, for example, here we're going to take the first equation and set it equal to 0. So what's called the x nullclines are found by setting the dx dt equation equal to 0. So in other words, we're going to set 2x minus x squared minus xy equal to 0. And we can solve for this. The easiest thing to do is to factor out an x. So that'll give us this. And of course, what's going to make this 0 is going to be anything that makes this 0 or this 0. So the nullclines one of them will simply be x equal to 0. And then we'll set this equation equal to 0. 2 minus x minus y equal to 0. And we'll set it as y equal a function of x. So we'll solve this for y equal, let me write it this way, minus x plus 2. So those are our x nullclines. And we're going to plot these here in a minute. And then we'll have our y nullclines. And they're found by setting this equation equal to 0. And so it'll be 5y minus xy minus y squared. If you're able to, it always makes it easier if you can factor out one of the variables. And so this will be 5 minus 4x minus y. So this time we factor out a y. And once again, what's going to make this 0 will be if that's 0 or this is 0. So the nullcline, the y nullcline is going to be y equals 0. And the other one will come from this being equal to 0. And again, if we solve for y in terms of x, we end up with minus 4x plus 5. So now we've got have our nullclines. All we have to do is to go ahead and plot them. And so plot, these are just simply lines, of course. So we can just plot those on graph paper. And which is what I did. I did it first by hand. And then, so I did it like this. The scale was kind of funny. Obviously, this one is the y equal minus 4x plus 5. And this is the other. And then what I ended up doing, I ended up using the computer to plot them. You probably plot them or whatever you like to do, or you could just draw them. and it looks a little bit neater that way. And also, I stretched out the x-axis so I could fill up the page. But in any case, all I did was draw this one. This was a y equal minus 4x plus 5. And then I drew this one here, y equal minus x plus 2. That's this line here. And then, now let's just maybe mark these temporarily. So the x nullclines are going to be, again, this one is the x nullcline. And also, notice that x equals 0. That's an x nullcline. So let me just mark it over here. And then finally, y equals 0 was a y nullcline. That would be down here. Like this. So again, I marked these. This is an x nullcline. This is an x nullcline. That was x equals 0. This is a y nullcline, and that was at y equals 0. And this is a y nullcline at y equal minus 4x plus 5 is a y nullcline. So be sure to mark all those. Then the critical points, these occur where the x and y nullclines intersect. And it's important to notice that it's where the x and the y nullclines intersect. So for example, this point up here, where the y nullcline and the x nullcline intersect, this is a critical point. And let's check some others over here where this y nullcline and this x nullcline intersect. That's a critical point. Now, notice here we have an x nullcline and an x nullcline. This is not a critical point because these are the same nullclines. This is an x nullcline. This is an x nullcline. So that's not a critical point. Let's see, where else do we have? Over back here. This is a critical point. Because we have a y nullcline and an x nullcline here. And let's see, this is a y nullcline and a y nullcline. This one is not a critical point here because these are just two y nullclines. And now over here we have an x nullcline and a y nullcline intersecting. Back here, so this is a critical point. Like this. So what do we have? The critical points are going to be 0, 5. Was this one up here. Then down here, 0, 0. Over here was 2, 0. Now this point here, to find that, we could find where this line intersects this line. We could do it, with equations, but looks like by observation, that point is going to be 1, 1. And let's just test it. When you put 1 in here, you get, when you put x equal 1 here, you get y equal 1. When you put x equal 1 here, you get y equal 1. So they do intersect at this point here at the point 1, 1. Like this. So we have, these are our 4 critical points. Let me just write those down. 0, 0, 2, 0, 0, 5, and 1, 1, like that. Now the critical points make both dx dt and dy dt 0 at the same time. Make both at the same time. Next, we're going to analyze the critical points. So let's analyze the critical points. And first thing we want to do is find the Jacobian. So we're going to need to call this, or let's call this maybe F1. That'd be like our first equation. That was 2x minus x squared minus xy. And call the other equation F2. That was 5y minus 4xy minus y squared. Again, all I did was take our original system of differential equations. That's F1, that's F2. And then for the Jacobian, the Jacobian is found by, and let me call it J. You can call it really whatever you like. So this is going to be the derivative of F1 partial with respect to x, and then partial with respect to y. Remember, when you're doing the Jacobian, you're going to always keep the same function in the first row, and then take the derivatives with respect to x and y. And then in the second row, you work with the second function. And again, take the derivatives with respect to x and y. And so let's do that here. So we're going to have derivative with respect to x up here is going to give us what? 2 minus 2x and then minus y. Derivative this with respect to x. Then derivative this with respect to y is just going to give us negative x. Then go to the second equation, derivative with respect to x. This would be 0. And over here, that's going to give us minus 4y. And then 0. Then a derivative of this with respect to y is going to be 5 minus 4x minus 2y, like that. And let me just call this equation star. And we're going to test each critical point. So the critical point, let's take them one at a time. Again, one of them was 0, 0. Sub into equation star. That's going to be as 2, 0, 0, 5. And to remember, when you have a diagonal matrix or a triangular matrix, the eigenvalues are just along the main diagonal. And so in this case, you can just read them right off. Now, if you forgot that, you're actually calculating them, but that do a lot of work for nothing. So the eigenvalues are 2, and 5. It doesn't matter which one you call the first one, the second one, but I just marked them here. Again, these are the eigenvalues. And since at least one of these is positive, this is an unstable node. And then let's do the next point that we had. The next one was 2, 0. So let's check the critical point at 2, 0. Sub that into our equation, our Jacobian. We have to do a little bit more work this time. So let's see. So we put 2, 0 into here. This is going to give us a 2, and that'll be 2 times minus 2, and that's going to give us a minus 2 because that's going to be 0. Minus 2. Then let's see if we put 2 over here, that's going to give us minus 2. And down here, we put 2, 0 here, y is 0, so that's going to give us 0. That's nice. And then over here, we're going to have 5 minus 8 minus 0. That looks like minus 3. So just double check. I put 2, 0 in here and got minus 2 because this was 2 minus 4 minus 0. Put 2, 0 here. That's just going to be minus 2. I put 2, 0 here. That's going to be 4 times 0. And 2 and 0 here. It's going to be 5. Minus 8 minus 0 this. So once again, we have a triangular matrix, so we can read the eigenvalues right off the diagonal. And so this time we have a stable node. Because they're both negative. And let's look at our other critical point 0, 5 and substitute into here. And we put 2 minus 0 minus 5. That looks like minus 3. And over here, when we put 0 in here, we get 0. Then over here, we have minus 4 times 5 is minus 20. And over here, we have 5 minus 0. And that looks like minus 2 times 5 is minus 10. So it looks like minus 5. Like this. And so the eigenvalues are minus 3 and minus 5. And so in this case here, once again, they're both negative. So it's a stable node. Both negative. They're both negative. It's a stable node like this. So finally, we have one more critical point. That was a critical point 1, 1. And again, sub this into equation star. And let's do that. And so again, if we put a 1, 1 into here, and let me move this all up a bit. That's going to give us 0, and then minus 1. And then over here, minus 1. Then over here, what's that going to give us? Minus. Then the last two are minus 4 and minus 1. When you put put 1 here, that's minus 4. Then 5 minus 4 is 1 minus 2 minus 1, like this. So for this one, we have to do a little bit of work since it's not a triangular matrix. And you can find the eigenvalues in the standard way. I'm sure you know how to do that by now. Though for a 2x2, there's a little trick you can use to find your characteristic equation more quickly. It can end up being, again, this just works for a 2x2. It's going to be lambda squared minus the trace times lambda plus the determinant and set that equal to 0. And so remember, the trace is the sum of the diagonal elements. So it's minus 1, going to be minus 2. And then, of course, the determinant is going to be minus 1 times minus 1 minus 4 times minus 1. So it's going to be 1, that's going to be positive 1, minus a positive 4. So it's going to be a negative 3. So then our characteristic equation, as I said, is going to be minus the trace plus the determinant set that equal to 0, and that's the same thing as lambda minus 3 is 0. And actually, this one, you could use a quadratic formula to find lambda, though in this case, it looks like it actually can be factored. We need two numbers that multiply to give us minus 3, but they have to add to give us a positive 2. And so it looks like that works. So it looks like our eigenvalues are going to be what satisfy this. So it's going to be 1 and minus 3, like this. And this is actually going to be unstable because one of them is positive. And actually, it ends up being a saddle point because one is positive and one is negative. So we can have an additional description for this one. So the bottom line is we have two stable nodes. We're going to see this a little bit later, but the solution is going to tend to be attracted towards the stable nodes. Like here, this was a stable node 2, 0, and there was a stable node here at 0, 5. So the solutions are going to be attracted to those points, and that we'll see that a little bit later. Next, we're going to look at the flow trajectories. That is the flow direct trajectories along the nullclines. So let's once again take a look at each nullcline. And we want to see what dx and dy looks like along each of these nullclines. And of course, by definition, the x nullcline is going to make dx dt 0. And then the y nullcline is going to make dy dt. Well, it won't make that 0 necessarily, so we'll substitute into that. So we're going to substitute x equals 0 into here. Substitute x equals 0 into here. And that's going to give us 5y minus y squared, which to help us work with this, we can factor out the y again. 5 minus y times y, like that. So again, all I do is put the nullcline into the dy dt. That made that 0. And then we have 5y minus y squared, factor out. And now we want to see how, if we take some points along here, we want to find out how this dy dt changes. And let's take a look, and we're looking along the nullcline x equals 0. So now we want to look in places where there's different regions. So what I'm trying to say here is that now actually this is also an X nullcline, but let's right here, let's check in this region here and check in this region up here. So we want to take points along x equals 0 and try y values. Let's try y equal 1 and y equal 3. And so let's make a little chart here, maybe even. Now we know all the points we're picking, x is going to be 0. And let's find y. And as I said, let's pick a point here, y equal 1. And let's pick a point up here, y equals 3. And let's put them in here. We all only want to see if we're going to positive or negative. And so this is going to be 1 times 5 minus 1. That's going to be 4. So that's going to be positive. And then we put 3 in here. 5 minus 3, which is positive 2, times positive 3. That's also going to be positive, like this. So that's telling us that along the nullcline x equals 0, dy dt is going to be positive. That means we're going to go in this positive direction. Y is going to change in the positive direction like that. And let's look at another nullcline. Again, this is going to be the other x nullcline. So let's look at this one. Remember this one we found y equal minus x plus 2. Once again, we know that that's going to make the first derivative 0. So then we want to substitute this then into the dy dt. So let's look at this. Now we have a couple ways we can do this. It looks like because we have all these y's here, it might be easiest just to substitute in for x rather than substitute all these places we have y. You could do it either way. It would just get much messier the other way. So what I'm going to do over here is I'm going to solve this for x. So solve this for x, and that's going to end up giving us what if we bring x here, that'll be minus y plus 2. That way, when we substitute into so now I'm going to substitute this into our original dy dt. So I'm going to put x, substitute for x right here. So I'm going to put minus y plus 2 into there. So I did that. Then multiplied this all out and got this. And then this is going to be 4y squared minus y squared. That'll be 3y squared. And this would be 5y minus 8. That'll be minus 3y, like this. Then we can actually go one step farther and factor out a 3y. And that'll leave us what, y minus 1, like this. And again, we can make a little chart over here. And we only have y's here, so we don't even need to put anything for x. So again, we're interested in what dy dt is doing because we know dx dt is 0. So we want to know what dy dt is going to be. So again, it's good to take a look at that nullcline. So let's take a look at that. We're working along this nullcline right here, y equal minus 2 plus x. And so we want to be sure to get something. Now notice here is a critical point, so it's going to change. There could be a change from here to here. So let's look first along here somewhere. That would be anywhere where y is like from 0 to 1. So let me put maybe half in here. Put a half over here. That'll be 3 times a half. And then 1/2 minus 1. So this is going to be negative and positive. So that's going to be negative along there. So that means that along this nullcline here, it's going to be negative. And let's check another point. Let's go to some point. So over here somewhere between y, wherever we're past this critical point, somewhere between y equal 1 to y equal 2. Let me do y equal 1.5. And so, again, this is going to be positive. And this time we're going to have 1.5 minus 1. So that's going to be positive. So those are both going to be positive. So that's going to be positive like this. So again, what does that mean? Let's draw those over here. So we're told, again, remember dx dt is always 0. So the only change is going to be in the y direction. And in this region here, it's going to be negative. So this is going to go down. I don't know how many of these you have to put in, just get an idea. It's going to be going down like this. But then when we're over here, it's going to be positive. Like that. So again, it's going to be going straight down here, straight up here. So let's do another one. So now for the nullcline y equals 0. And again, that's the one along here. And so again, since that's a y nullcline, we already know that dy dt is going to be 0. But now we're going to have to put this into our other equation. So put y equals 0 into this equation here. So that's going to leave us at 2x minus x minus 0. So that's going to be our dx dt is going to be 2x minus x squared minus x times 0. And again, we can factor this minus 2 like this. So this is what we're going to look at this now. And again, you can make a little table here. And again, we don't have to worry about the y values, no y values. Let me put it down anyway. We know dy dt is 0. Now we're interested in dx dt. And so again, it's always good to look at our picture to get an idea where we're at. So if we're at y equals 0, now usually you don't have to check. You won't have to check since either both y nullclines where they intersect. So we may or may not have to check here. Let's just check this just to be sure. Actually, now that I think of it, yes, we probably don't have to check it. We'll check it anyway. So in other words, we'll pick a point along here and pick a point along here along this y nullcline, the nullcline y equals 0. And again, since this is a y nullcline, there shouldn't be any change here, but just to be sure we didn't make a mistake, let me try this. So let me pick a point over here. Let me pick 0.5, x of 0.5, and put it in here. You can see this is going to be 2 minus 0.5, that's positive, times 0.5, that's positive, so that's going to be positive. And then let's pick a point over here, maybe 1.5. And this will be 2 minus 1.5. That's going to be positive times positive. That's positive there. So it looks like those ones will all be going in the positive direction. And let's also pick something maybe past here. Let me pick 2.5. And so 2.5. Now here you can see when you pick 2.5, this is going to be negative times positive. So that one's going to be negative. So we should then, so what we're going to have is all along here, these are going to be positive. And I realized now I should have made my graph a little bit bigger, because on this side over here, if we get past 2, these are all going to go back in this way back towards this point. So when you get past 2, you go back towards it. But mainly, so these ones are all going to go this way. And if it's beyond this point, they're going to go in this way. Though we're mainly just interested just in this region, so we're not too concerned about what's happening here. So let's see, we have just one more nullcline to look at. That was the nullcline y equal minus 4x plus 5. Here's another nullcline. And once again, that was a y nullcline, so we know dy dt is going to be 0. And then we're going to have to go back to our original equation. And this is going to be dx dt. It's going to be 2x minus x squared minus x y like this. So again, we're going to substitute into here. This time we can just substitute it as it is because these are already all x's. So let's go ahead and do that. I'm just substituting this into here. 2x minus x squared minus x 4x plus 5. 3x squared, and this will be minus 3x And we can factor out a 3x, x minus 1 like this. And once again, look at our picture, get an idea where we're at. So that's going to be this y nullcline right along here. So we're going to have to check in this region here. It's going to be 1 point. Then after it intersects this, we need to pick a point up here somewhere. So let's maybe pick the point. Let's see, what do we have? X's here. So we'll have to pick a point somewhere here. Let's pick maybe the point 1.1, which would be like right here. I really don't even need the y column, but so we want to put 1.1, and also so that would give us a point, somewhere in this region. That give us a point somewhere in this region right here. Then we want to pick a point somewhere in here. We can pick almost anything we want along here. Let me pick maybe 0.5. And see what we get when we put 1.1 in here. This is going to be positive. 1.1 minus 1, that's going to be positive. That's all positive, so that's going to be positive. And then we put 0.5, that's positive. Now 0.5 minus 1 is negative, so that's going to be negative like this. So that means that in this region here, dx dt is going to be positive. Looks like it's going to go in that direction. And up here, it looks like it's going to go in this direction. Remember, it's going this direction because there's the y component 0, dy dt 0, so it's going to be just horizontal. So it's going to go like this. Now, one thing we kind of see here is, what this is kind of telling us is if we start like a point in this region here, and let's say, we start an initial condition here, and then we have a solution. If the solution tries to go this way, notice it's going to be repelled back in. Or if it's the solution wants to go this way, it's going to be repelled back in. So everything's pointing towards this internal part of this region. And same thing, if it goes towards the edge here, it looks like it could be pushed up this way. And so it doesn't look like anything that starts here can get out. So nothing can get out. See, it's always pushed back in because everything is pushing towards the internal part of this region. Even here, it's just kind of just pushing up towards this point here. So this is called an invariant region. Any initial condition that starts in here, the solution will stay in here. Now let's look down here. Notice this is another invariant region because everything is pointing in towards the center of this region. So no matter where a solution tries to go, it's going to be pushed back in towards the center of the inside this region, or towards this critical point out over here. So it can't cross. Like, see what's happening is it can't cross here because it's always pushed back in or pushed along this line here. Now notice, so this is also, it's called an invariant region. Anything that starts here has to stay here. Now, but notice these other regions are different. Notice if something starts here and it heads toward this boundary, look, it'll get sucked right into here, right into this region up here. Or if something starts over here, it's going to get sucked this way, because if something is here, it can get out. In fact, it will get out. It'll get out here. Or for something that starts over here, maybe it's going to get pulled into this region. Maybe something starting here maybe gets pulled into this region. So here's a somewhat fancier picture of what I just drew by hand. I took some of the notation out, but you can see like our invariant regions, and you can see clearly how those arrows are pointing in either towards the invariant region, or again, if you happen to say come close to this line over here, you'd see things are going to get pushed up to this critical point up here. Remember, this was a stable critical point. So again, anything that's like starts in here will stay in here and probably eventually be pushed up towards this critical point. Or down here, you can see if something gets towards this line, it's going to be pushed up towards this critical point. So that gives you a nice, clear picture of the invariant regions here. The next thing we want to do is take a look at, see what happens if we start at some points on this graph and see where we end up. As I mentioned before, if you start in an invariant region, you will end up staying there and going towards the critical points. If you start outside of one of the invariant regions, you'll likely be pulled into the invariant region and towards a critical point. So let's take a look at starting at this point right here at 0.8 and 1.5. Now notice we're going to start here and then watch where the solution moves from here. It's not going to move towards this critical point over here because this was an unstable critical point. Notice, see what happened is it moved towards this critical point up here. And also it stayed within this invariant region. Remember, this was one of our invariant regions up here. So it started here and then went up toward this critical point. Again, it would never go outside this invariant region once it starts inside. Now I'm going to start way up here at 0.94 and 1.2, and let's watch where the solution goes. So we're starting here we're starting real close to this critical point. Remember, there's a critical point over here at 1.1. But we're starting within this invariant region, but we said this critical point was unstable. So we're anticipating the solution's not going to go towards that point, and it doesn't. You see what happened? It goes, started here, and then it went towards this stable critical point up here. So again, this illustrates a couple of things. We determined this is an invariant region. Nothing that starts here will leave here. And then when you have a solution, it won't go towards this unstable critical point, which was 1, 1, even if you start real close to it. Instead, it'll go to this critical point up here. Now let's pick something in this region down here. Remember, we determined this was also an invariant region. And so we will start here. And once again, it's not going to go to the other invariant region. It's going to stay in here somewhere. So it's going to go to a stable critical point within this region. And that's going to be this point over here. Remember, we determined this point over here at 2, 0 was a stable critical point. Let me start, let me think of something. Start something maybe over here somewhere, maybe 1 point x equal 1.1, and what y maybe equal 0.9. 1.1 and 0.9. So again, we're starting, let's see, we're starting way up here. Did I get too close to the line? In case we're starting way up here, let's see where the solution goes. We know it's not going to go towards this critical point at 1, 1. We're anticipating it goes to the critical point down here, which is at 2, 0. And so we're starting here, and there it goes. It goes down towards 2, 0. So it starts here in this invariant region and goes towards a critical point 2, 0. And so again, anything that starts in these invariant regions, let me just do one more. Let me do this one here, 1.2 and 0.5. So now this time we're starting at this point over here, 1.2 and 0.5. And we'll see where the solution goes again, where we know this is an invariant region. So the only critical point it could possibly go to is the 2, 0 again, because the critical point 1, 1 was unstable. And you can see that's exactly what happened. It started here and went down towards the critical point 2, 0. So this time let's try something outside the invariant region. Let me start with this point down here, 0.4 and 0.5. And so now it's not going to go towards a critical point 0, 0, because we said the critical point 0, 0 was unstable. So let's see where it gets sucked into. Oh, there it goes. It started here and went up, got into this invariant region and got to this critical point here. I wasn't sure if it was going to go into this region. And again, once it gets into the invariant region, it never is going to get out, because that's why it's an invariant region. And it went this way. I wasn't sure it was going to go up here in this region, or maybe it was going to go down into the region into the lower right. Maybe let's pick a point closer to this lower right region and see if it gets into that one. This time we're going to start down here at 1 and 0.5. And we'll see which invariant region the solution goes into. Again, it could go into this upper one, but I think it's going to go into this lower right region here, and then head towards a critical point 2, 0. And that's what it did. See, it started here, and it went down into 2, 0. And again, there are ways you could, if you did a lot more analysis, you could find out which direction it's going to go. But I'm just sort of doing it by trial and error. Let me do maybe another one. Let me do 0.8 and 0.5, see what happens. So this I'm starting down here at 0.8 and 0.5. And we'll see which region that it goes into this time. Again, it could be the upper left region or the lower right region. And again, this time it went into the lower right region and headed towards the critical point of 2, 0. So that gives you an idea what happens when you're outside the invariant regions. The points will usually that are outside get sucked into the invariant regions and then towards the stable critical points. This time I'm going to start way out here at point 1.8 and 3, see what happens this time. Oh, there it goes. So this time, if we start out here at 1.8 and 3, the solution ends up going down into this invariant region and down to the critical point 2, 0. And let me try one. Let's see what happens if we start maybe up here 1.4 and 4. Let me try that. This time I'm starting up here at 1.4 and 4. I want to see which way it's going to go. Again, if we could analyze this more and predict it, but I'm just kind of experimenting, see. There it goes. So this one went into this invariant region over here and went up to this critical point here. But in any case, this is how you would do the Nullclines to figure out what the invariant regions are. Again, nothing that starts in the invariant region leaves there, and points outside the invariant regions will usually get sucked into the invariant regions and towards the critical points in those invariant regions.